Hi, Tom. A little earlier today, I was talking with one of our customers, and he was asking questions, and I'll ask these questions to you. He was trying to come up with a strategy for testing a large titanium shaft. It's a hollow shaft that's used in a helicopter, but the shaft is about 10 feet long, and he wanted to measure thrust in it. So I'm curious at what you would recommend for a large shaft made out of titanium and measuring the thrust in that shaft.
Well, Daryl, that's an excellent question. I would probably go with something we call a full Poisson's bridge, where we put two gauges in the axial direction and two in the Poisson's direction, and wire those up so that the two axial gauges are exactly 180 degrees apart from one another.
Okay.
If you do that, then it'll cancel the bending, and this will give you the ability to give you about 2.6 times the strain that's in the axial direction. It'll multiply that, if you will.
Okay, so if I had, say for example, I had enough thrust on it to generate, say, 100 microstrain along the axis, then the total output I would get, you're saying, is about 2.6 times more than that?
About 260 microstrain among
Wow.
friends.
Wow, so,
Now, at that low a strain level, your resolution will be quite small, and it's usually the problem you have with these making a structural element into a transducer so you can measure a load. A lot of times they're designed such that the strain levels are so low that you might not get a very good reading. But if you weaken the structure or somehow make it to get, so you have nominally about 1,000 microstrain in tension or compression, that'll give you probably your best resolution.
another interesting part of this one is that he was expecting temperatures up to about 300 degrees Fahrenheit. So, what would you recommend for an adhesive for measurements up to about 300 degrees Fahrenheit? I think one of the potential concerns was how much heat they could actually add to this large shaft.
Well, typically you'd want to do something like the M-Bond 600 or 610. Those are very thin epoxy phenolic adhesive systems designed specifically for transducer applications and or higher temperature applications. The one drawback is you now have to take that M-Bond 600 up to 175 degrees Fahrenheit and leave it there for 4 hours while it's curing. So you'll have to come up with some strategy for locally heating that.
What do you think about using a vacuum applicator to do that? I think that was the route they were planning on.
As a matter of fact, a large number of our customers use those. There's a company that makes a vacuum applicator that's got a little heating element in it.
Okay.
And that little heating element has a controller and allows you to set the temperature of that bond line to that 175 or whatever temperature you want it to be. Now, you do have some limitations there. If you've got a huge shaft that's out in the cold of Bemidji, Minnesota in the winter, the chances of your heating up that shaft very good are not too terribly good. But normal circumstances where you got a 30-degree day or a 40-degree day and you need to cure something, those those vacuum operated applicators tend to do a very good job for that.
Okay. What about protective coating? As we were walking, or not walking, but discussing it, one of the things about it was that it's going to get hot, but it also may see some oil. It might see some grease from gear train and those sorts of things. So what would you suggest as an environmental coating for that?
The one that comes to mind is GA61. It's a two-part filled epoxy, and that can go up to temperatures upwards of 500 degrees Fahrenheit, 600 degrees Fahrenheit. The one issue with it, though, however, is you have to put some fiberglass cloth in it to stabilize it. Like all epoxies, when it heats up to cure, it expands. And then if you don't have the fiberglass cloth in it to stabilize it, as it cools off, it breaks itself apart. Kind of like watching a mud puddle in the summer as it dries up. You see the clay on the bottom of it break into little plates.
Yeah, okay.
That same thing would occur without the fiberglass embedded into it. It does require an elevated temperature cure. And you also have to be careful because you're on a spinning shaft that the balance is maintained. So you may have to put down the GA61, get it cured, and then maybe machine it away to make it a uniform thickness.
So just to summarize, type of bridge circuit for this thrust measurement we said was a full Poisson bridge.
Yep.
Type of adhesive system, M-Bond 600 that can easily go to the 300 degree Fahrenheit temperature, and then a really tough environmental coating to protect the gauges when they're going to get hot, but also be exposed to oil and grease and things like that. was the GA61.
That's correct. That's pretty much the application you've described. Now, we also have other places where people want to make a spring or a transducer out of a part so that they can use that data to feed their finite element model with the boundary conditions. They've made assumptions, but sometimes you have to verify those assumptions with putting a transducer in your structure by making a bracket into a transducer or some other way of doing that. And we have a couple of articles. One's called Force and Torque, the other's Custom Transducer Design. And if you send me an email, I'd be happy to send those two articles to you, and that'll give you the basics behind how to build your own homegrown transducer.
Fantastic, fantastic. Thank you, Tom. Appreciate it.